Anyway, enough of that. We've got a message from Florence which we'd better pay attention to. By the way, please make sure you've got both of the bits of paper that are going around. Messages from Florence are always important. Let's see what this one says. Relax, guys, relax. Dear Connor, if you want my help setting a tiny test, you'll have to help me finish making some traffic lights. I'm sick of Lord Sir nearly running me over in his roller when I'm crossing the road to the bus stop. I've got the light box ready, I just need the control circuit. I've left you a pair of flip-flops. I wonder if she's concerned about my footwear. Says Florence, but she's left me these things. And I'm wondering what they're about. So we might need to figure that out. Oh, there's a PTO. PTOs are always important. She says, D is edge triggered and obeys the law. Q of t plus 1 equals d of t. I've left you a clock and some NOR gates. So let's see what else was in the envelope. Oh, there's this diagram in case Florence thinks I haven't remembered how traffic lights work. Does this ring a bell, traffic lights? This is the sort of sequence that the lights should light up in. If we're starting with green, then it'll go to amber, and then it'll go to red for stop, and then it'll go to red and amber to get ready for go, and back round again. Does that ring a bell? So we need to make a circuit that does that sort of thing. And somewhere or other, maybe they're still in the envelope. Yeah, I've got a couple of NOR gates. And this funny thing here, I wonder what that is. So we've got a component which has an input called D and an output called Q. And there's this thing which generates a signal which seems to pulse up and down. And there's a little number called T, which might be time, that is labeled 0, 1, 2, 3. And we've got an equation that says Q of t plus 1 is equal to d of t. So we better, and some message about d being edge triggered. So we're going to need to learn about these D things. This D thing, by the way, is called a D flip-flop, and it's the only sort of flip-flop that I have ever anything to do with, at least when I'm teaching. Right. So let me try and explain what happens with the help of Florence's handy equation. So these things, I mean, you've seen the tiny machine works in steps through time. Well, a D flip-flop is a very important part of the tiny machine. In fact, they're a very important part of lots of machines. Right? There are at least 80 D flip-flops inside the tiny machine. There are at least 1 trillion D flip-flops in that thing. D flip-flops are how memory get made. Okay, so how do they work? Well, the idea is that time steps not continuously, but in discretely numbered phases, 0, 1, 2, 3, 4, 5. And the way a time step is signaled is that the clock signal goes from from logic 0 up to logic 1, and then back down again. So in every clock, so a clock cycle is just however long it takes for the clock signal to go from 0 up to 1 and back down to 0 again. That's called a clock pulse. So there is one time step for each pulse of the clock. And what happens with a D flip-flop is that it pays attention to its input when the clock goes from 0 up to 1, and it changes its output when the clock goes from 1 down to 0. That's to say, it's the changes in the clock that matter. Clock goes up, look at the input. Clock goes down, look at the output. So what happens is, the input at the beginning of the clock cycle determines the state of the system at the end of the clock cycle. So that's to say, the rule for the D flip-flop says that whatever comes in at D at a given time t, that's what comes out from Q at time t plus 1. And that's to say, there's a signal that arrives at some time, and it's remembered one tick later. It comes out, so it arrives at D at a given time, and it comes out again from Q one tick later. You'd be wanting one of these maybe.
Yeah, I was wondering whether.
Right, okay, so let's have a go at following the rules. I've got myself some pens. Let's do the base bit. Let's see what happens here. Okay, so you can see that in this circuit, we've got a clock signal coming into this wee triangle here. So the wee triangle on a flip-flop circuit always signals where to put the clock in. And then it's got the D input and the Q input. So let's figure out what we know. So I'm already telling you that the value of Q at time 0 is 0. We have Florence's equation, which is Q of t plus 1 equals D of t. And we know something else as well. You can see that our input signal X is wired to the input D of the flip-flop. That tells us in particular that those signals always have the same value. They're connected by a wire. So we know that D of t is equal to X of t. So now we should have enough information to figure out, because I've told you what the value of X is at each time, what happens with the flip-flop. So can you figure it out? Let's do this one together. So at time 0, X is 1. So what's D? Also 1. So at time 1, what will Q be? Well, Q of t plus 1 is D of t, so in particular, Q of 1 is D of 0. And we know D of 0, so it would be 1. That's to say, the value that came in at time 1, so at time 0, comes out at time 1. Okay, moving along. At time 1, what happens? What's D of 1? 0. So what's Q of 2? 0. Alright, what's D of 2?
0.
What's Q of 3? I heard 0 and 0 is right. What's D of 3?
1.
What's Q of 4?
1.
So, what we've got going on here is that because they're connected by a wire, D is always a copy of X. And because this is a D flip-flop which obeys this law, whatever D is at one time, Q is one tick later. Everybody see what's going on? Whatever comes in to D at one time comes out at Q one tick later. Okay. Over the page, now your turn. It's a good job I've got 2 copies, because I'm using ink that runs through. Right. This time, as well as delivering an output from Q, the Q signal is looped back around into a NOT gate, and that's what's feeding the input of the flip-flop. So I'm telling you that the flip-flop starts with Q being 0. So Q of 0 is 0. Q of t is 0 when t is 0. So you should be able to figure out what happens from then on. Why don't you give it a go? See if you can figure it out. Let's see what we can do. Right. You can see that because Q is wired round to D through a NOT gate, at any given time, D is going to be the logical negation of what Q is. So what's D of 0?
1.
1. So what's Q of 1? Yeah, usual deal. Whatever comes in at D comes out one tick later at Q. Okay, so what's D of 1? So what's Q of 2?
Usual.
So what's D of 2?
1.
So what's Q of 3? 1. So what's D of 3? So what we've got here is a circuit that keeps switching between 0 and 1 at every tick of the clock. Does everyone see why that's happening? And also that, although it looks weird that this circuit has a loop in it, there's nothing weird going on because this circuit, the D in a D flip-flop stands for delay. So what we're getting is that the new input, the input depends on the current value of the output, but that doesn't affect the current value of the output at all. It affects the next value of the output. So you can see causality in this circuit is going from here to here, down to here, down, up. There's no problem, there's no cycle in terms of what depends on what as far as the data are concerned. You can just completely calculate it. Yeah? We're figuring out, at any given time, we can figure out D from Q, and then that tells us what the next Q is. Yeah? Okay, so just to see again, right? D of 0 is 1 because that's Q of 0 coming round into the NOT gate and a 1 coming into D. And then that doesn't change what Q of 0 is, but it does say what Q of 1 is. And then we can figure out the same thing next time. So we have to run a perfectly ordinary circuit at each time step, and then the flip-flop tells us what information is carried from each time step to the next. That's to say, it behaves like a memory. Okay. Let's do one more of these. And I'll leave the last one as a piece of fun. Okay, so this is a slightly weirder circuit, but not much. It's got 2 inputs. One is called co for control, and one is called da for data. And you can see that the control is controlling a mux, and it's deciding which of 2 things is being sent into the D input of the flip-flop. If the control is 0, the mux will choose the old Q value. If the control is 1, the mux will choose the current value coming in from data. So I've given you that the initial value of Q is 0, and I've told you what the control and data signals are at each time. So can you have a go at figuring out what happens? Again, feel free to talk it through with your neighbours. Shall we see how we can get on with this? Right. At time 0, the mux has to choose between Q or the data line. Which is it going to choose? It's going to choose Q. So that means D is, well, they're both 0 anyway, so that's fine. And what does that make Q of 1? Okay. At time 1, what's the mux going to choose? It's going to choose data, which means D is what? So what's Q of 2? Alright? At time 2, what's the mux going to choose? It's going to choose Q, which is going to make D what? And what's that going to make Q of 3?
1.
Okay. At time 3, what's the mux going to choose?
0.
Well, its controller is 0, so which line is it going to choose? It's going to choose Q, so what's D going to be? So what's Q of 4? Okay. When at time 4, what's the mux going to choose? It's going to choose the data line, so what's D?
1.
So what's Q of 5? Okay, at time 5, what's the mux going to choose? It's going to choose the data. What's that making D?
0.
So what's Q of 6? At time 6, what's the mux going to choose?
0.
It's going to choose Q, which means D is going to be 0. What does that make Q of 7?
0.
Okay. And at time 7, what's the mux going to choose? It's going to choose data, which means D is what?
1.
So what's Q of 8? And we can also figure out, just to finish off, at time 8, what's the mux going to choose? It's going to choose Q, so D is going to be 1. So what's going on here is that every time the control signal is 1, the memory gets updated from the data signal. But whenever the control signal is 0, the memory stays what it used to be. So what we have here is a memory that we can update whenever we like. If we send it a 1 on the control signal, it'll update to whatever we send on the data signal. And if we send it 0 on the control signal, it'll just stay what it was and continue remembering the old value for as long as we don't want to change anything. So that's exactly how the bits in the memory of the tiny machine work. When you get, so each bit in the memory is going to be something like this. It will remember its value for as long as you like, until something, usually an STA operation, tells it to be different. And then it will say what to change it to, and the old value isn't there anymore. So the bits that are being remembered are this one, which is remembered for this long, and then this one, which is only remembered this long, this 0, which is remembered that long, and this one, which at least, well, is remembered at least that long. Okay? Is this making some kind of sense? We got some logic that we use to tell the D flip-flop what it ought to be remembering. Okay, so I'll leave you this one to take away, but you'll notice that I've written it backwards for a reason. And you can look at what the D flip-flop is doing. It's taking the carry output from a full adder and feeding it round as an input to the full adder in the next time cycle. So it's like whatever comes out of the carry at one time gets fed in as something to add at the next time. Does that remind you of doing anything? Good. That's why we're working right to left. This is an adding machine, but the two numbers to be added, instead of coming in each bit on a different wire, each bit comes in at a different time. The 1s, the 2s, the 4s, the 8s, the 16s, the 32s, and so on. And you remember the carry from the 1 long enough to add it to the 2s. You remember the carry from the 2s long enough to add it to the 4s, and so on. So this shows that you can do adding with just one adder, but over time rather than by making a big circuit. So here we're spending time rather than silicon, and the bits arrive one at a time rather than all together on a big wide pile of wires. But it's the same adding process. Okay, we better get back to Florence's puzzle to make our traffic light. We've got some idea what D does, but I've got this other component here which is called T, and I'm going to need to figure out what it does. Let's look inside. T is made by a bit of logic controlling a D flip-flop involving an XOR gate. So we better see if we can figure out what's going to happen. And the way we can do that, like any old logic gadget, is to write a truth table. But this time we have to be careful to explain what times are involved. So at any given time there's going to be an input signal, which I'm going to call big T of little t. And there's going to be the current state of the flip-flop, which is Q of t. And if we're lucky, we should be able to figure out what D of t is. And if we know what D of t is, we should be able to figure out what Q of t plus 1 is. Okay? So let's get on with it. We tabulate all possible inputs. Okay? So, if T and Q are both 0, what's D? At a given time T. So what will Q be at the next time? 0. If T and Q are at time T are 0 and 1 respectively, what will D be? 1. So what will Q of t plus 1 be? Also 1. How about if T of t is 1 and Q of t is 0, what will D of t be? 1, because that's what exclusive OR does. So what will Q of t plus 1 be? And if T of t and Q of t are both 1, what will D of t be? 0. So what will Q of t plus 1 be? Also 0. Okay, so we figured out what rules this component obeys. There's another way we can summarize that information, which is to write a thing called the characteristic table. And characteristic tables are usually shorter and clearer. They tabulate all the inputs, but they do not tabulate the current state of the flip-flop. So here we'll just have 0 and 1. But what you put in the output column isn't necessarily just a 0 or just a 1. It's a logical formula expressing the next state of the flip-flop in terms of the current state. So we're allowed to refer to Q of t when we fill this thing in. Okay, so here's how you figure out a characteristic table from a truth table. You need to look at pairs of rows, right? When big T is 0, that means we're in one of these two lines of the truth table. And you can see that if this is what Q of t used to be, this is what Q of t plus 1 will become. So, what's happening? Yes, in both cases, Q of t plus 1 is the same as Q of t. So we write Q of t as the formula in the output column of the characteristic table. Now let's look at the situation when big T is 1. That's these two lines. Here was Q of t. Here's Q of t plus 1. Now what's happening? It's being negated. So we write not Q of t in the output column of the characteristic table. So what we're saying is this flip-flop T has two behaviors. When it gets the 0 signal on its T input, it means the flip-flop state stays the same. When it gets the 1 input on its T signal, the flip-flop state negates, or some people use the word toggles. So this is T for toggle. And that is toggling. When T is 1. Okay. So now we know what our components do. We just figured it out by using the behavior of the D flip-flop and the behavior of XOR. Now we need to figure out how to make our traffic lights. Here's the sequence of signals we're supposed to get working. And we've got various bits and pieces. So we've got red, amber, and green lights. And we've got to control them somehow. There are 4 states of the system, as you can see. How many bits of memory would we need to represent what state we're in? Given that there are 4 states, 2 bits of memory will do fine. So it's just as well that we've got 2 flip-flops, because each of them can remember 1 bit. Okay. But next we need to figure out what the logic is so that our 2-bit circuit will control the flip-flops, will control the lights to make this pattern. Do you notice anything about the green light? It's only on once, and when it's on, what about the other 2? No. They're off. We have a handy NOR gate. So the green light is on exactly when neither of the other 2 is on. So if we can figure out how to control the red and the amber, we can just wire up the green to the NOR of those 2. So the problem's already got easier. We just have to figure out how to control the red and the amber. So let's see what behavior we want. Okay, so let's first of all just draw a table. If we know red at time t and we know amber at time t, let's figure out what should be red at time t plus 1 and amber at time t plus 1. Okay, we got 4 possibilities. So, possibility number 1. Red and amber are both 0. So what should they be next? 0 and 1. Red 0, amber 1. Okay. Now what happens when red is 0 and amber is 1? What's next? Red is 1, amber is 0. Okay. Now what happens after red being 1 and amber being 0? 1, 1, they're both on. And then what happens to red and amber after they've both been on? You'd think I did that deliberately. What we're really doing is just counting in a cycle through the binary numbers, through the 2-bit numbers. 0 goes to 1, 1 goes to 2, 2 goes to 3, 3 goes back to 0. Okay. So let's see what we can figure out. Let's look at the behavior that happens. When does A change? A changes all the time. That's to say, whatever A is the negation of what it used to be. Hang on a minute. What was that circuit doing? You can see every time it flips its state. So we could build, if we can build not from NOR, then, which I think we probably can by now, then we can certainly build amber. So let's start to build up this circuit. We said that green was going to be made by a NOR gate. I'm going to need blue tack for this job. Right. We said we got red. Once upon a time I had an orange pen, but I don't know where I put it. So I'll have black there. And here's red, here's amber, and we said that was going to be like that. So that's the logic that says green is the NOR of red and amber. And then we just said we want to build a copy of the circuit we had earlier. So here's D. And we said D needs to be controlled by a NOT gate. So we can do that and tie this thing's legs together. So that's the circuit we had before. So this says amber is, can you all see that as well as controlling the amber light, this Q via a NOT gate controls D, which means amber will alternate on, off, on, off. Okay, so now we need to look at a piece of paper which I have cunningly hidden from myself. What happens to R? Well, what happens to R when A is 0?
Same as amber.
Well, careful. So look at these two lines. How does R change when A is 0? Here it's 0 and becomes 0. Here it's 1 and becomes 1. When A is 0, R stays the same. How about when A is 1? These two lines. So we're looking here and here. A moment ago we were looking here and here. When A is 1, what happens to R? It's negated. You can see when A is 1, an R of 0 becomes an R of 1, an R of 1 becomes an R of 0. So that's to say, when A is 1, R toggles. When A is 0, R stays the same. So it's just as well that we have exactly the right thing which behaves like that. Right? We just said that it's the amber signal that controls whether the red signal should toggle or not. So we'll take the amber signal and we'll wire it into the toggle control of the T flip-flop, and we're nearly done. In order to make sure it all works in a timely fashion, all we have to do is wire up both flip-flops to the same clock. Okay, so I can't get it all because I can't zoom out any further, but you can see that was the right logic for getting green controlled from red and amber, and then this was the right logic to make amber flip every time the clock ticks, and this is the right logic to make red change whenever amber is 1. And if we go back to the traffic lights, you can see amber is off, on, and you can see that whenever amber is on, red changes, and whenever amber is off, red stays the same. So the behavior of the two flip-flops, the D for delay flip-flop and the T for toggle flip-flop, together with this extra bit of logic around, gets Florence her traffic light circuit. Now, I haven't told you how to make a D flip-flop. I've shown you how to make T from D. I'll tell you that on Friday. But between now and then, have fun. I'll make sure this picture gets sent somewhere. Can I have your 1-minute papers in the boxes, please? And just a word to say that this topic is peak difficult for semester 1 CS 106. After this topic it starts getting easier again, which I hope is at least slightly reassuring.